I'll start with a quick review for this book or course, Practical Physics for Non-physicists. I'm going to give this book 2 out of 5. It started very good about how everything goes and the fundamentals of physics, but then it got all too abstract and I wouldn't say complicated because it's a very complicated subject, but the fact that he says for non-physicists, I haven't felt that he did a good job of doing or transferring their information for not physicists. I haven't felt like he did a good job of it. I'm not a physicist, and I got lost in quite a few parts. So it got too abstract, too deep into some matters, and not deeply enough to other matters. So overall, if you're not a physicist, I would not recommend. If you are, maybe you don't need it. Anyway, let's see the notes. Reductionism, that is breaking things to smaller parts, isn't the only way to investigate phenomena. There is other ways, but that's one way science use a strategy science use to understand things is reductionism, is taking things into smaller parts. A micron is 10 to the minus 6 power, which is 10 divided by 6 zeros, which is 1/1,000,000th of the size of a bacteria. So that's a micron. Nanometer is 10 to the minus 10 power, which is 1/1,000,000th of the smallest size we can manipulate. So obviously we cannot manipulate a nanometer. And that's not, nanometer is the smallest things that we can, it's way, it's bigger than what we can manipulate. I mean smaller. But atoms are even smaller than that. They are 10 to the minus 10 power. So it's very, very small things we're talking about here. The nucleus is made out of 3 quarks. So that's one thing about the nucleus. There is quarks. We're still not sure what they are, how they function, but those are the quarks. Gluons are particles that glue particles together. So that's gluons. Quantum waves are showing probability where the particle is likely to be and where is not. Where is high, the probability is high. So that's a quantum wave. It shows probability. It doesn't show where the particle is. It shows where it's likely to be and where it doesn't. High probability shows that it has a higher probability of being there. Force in the distance could be thought of as throwing a ball or a photon, because it's hard to think about how force works from the distance. One way to think about it is throwing a ball, which is something we had a connection. We contributed something to the ball going where it goes. Every particle has an electric charge. The higher it is, the stronger the interaction. So all of them have some electric charge. Some of them have more, some of them have less. Symmetry is things to look the same way no matter the perspective taken. There is symmetry in certain parts, and that's why the meaning of symmetry. Conservation laws state that energy stays constant and can only change form. Same applies to momentum. There is no momentum is lost and no energy is lost. It can only transform into a different form of energy. Gauge symmetry states that the differences matter not the value. 0 to 1 or 3 to 4 is the same as long as the difference is the same. So that's the gauge symmetry. It doesn't matter where you start the gauge. You can start from 0, you can start from 5, you can start from 10, as long as the difference is the same. Side note, the course is extremely abstract. He didn't do, as I explained in the review part, he didn't do a good job of making things easier to understand. Part of the problem is that reading is not the best way of understanding physics, especially such abstract notions. Probably videos are doing much better. Gravity is a very weak force which is minuscule in comparison to electric force. Gravity is not a very strong force, especially in comparison to other forces. This goes in tandem. Gravity feels strong because we are close to a big planet where all atoms' gravity together create a strong force. We feel like gravity is strong. That's because we're standing on a planet where all the atoms have gravity together, and those create some strong force, but electrical force is much, much stronger. String theory claims that everything is made of strings, not particles. So there's the strings of particles, maybe, but everything is strings, and this eliminates infinity because there's a problem of infinity, and this theory is also more coherent because there is no infinities in the string. Stars move closer to us appear blue, while those who get farther appear red. So that's how we can know which stars are coming towards us and which are getting farther. That's it for the notes. Again, 2 out of 5. You didn't do anything. You did a good job of explaining concepts and ideas to non-physicists. So I would not necessarily recommend. Thank you.